entanglement properties, and it will be used for identity.
Yeah. Yeah, so Arnab was saying I was a student here. I did my 4 years of undergrad here, so it's really nostalgic to be here and to be giving a talk. Yeah, I was working with Aninda, so it's really nice to meet him as well. And thanks a lot, Arnab, for organizing this and introducing me. Yeah, so I'll be talking about entanglement entropy and the recent development on entanglement entropy of black holes, so on islands. So this is some work I've been doing with Marika Taylor over the past few years, and you can find most of the work in these 2 papers. So before proceeding further, feel free to interrupt me whenever you want if you have any questions, so we can discuss further and it can be more of a discussion. Yeah, so the outline of my talk will be as follows. I'll be discussing this measure called entanglement entropy, and then I'll motivate why one must study this measure and how to calculate this measure. And then I'll talk about what relevance it has for black holes. Yeah. So usually whenever you take a system, you do not know exactly everything about the system. So whenever there's an ignorance, you have certain probabilities associated with that. And with respect to these probabilities, you can associate information measure. So this basically measures the amount of ignorance. So here it's the Shannon entropy. So if you have a quantum mechanical system, a density matrix completely captures this, and you have the corresponding von Neumann entropy. So let us also quickly remind ourselves about a unique feature of quantum mechanics that is usually not there in classical mechanical systems. So we usually have non-local correlations in a quantum mechanical system. So what do I mean by that? If you take a state in a joint Hilbert space HAB, then you can't always factorize it as a tensor product state, as a state in Hilbert space A, tensor product a state in Hilbert space B. However, you can always do this in a classical mechanical system. So these are called entangled states. And let me take one such entangled state, and using the Schmidt decomposition, I can always write it as a sum of tensor product states. Now let me take a density matrix constructed using this. So I have a ket psi and a bra psi, and I trace out the degrees of freedom with respect to one of the subsystems. Then what I get is a mixed state. However, if I just take a completely unentangled state, so something like this, and if I trace out the degrees of freedom with respect to only A, then what I'll have is a pure state. So you can already see the degree of mixedness in the subsystem captures the degree of entanglement in the parent system. So if you can somehow quantify this degree of mixedness, then we can quantify the degree of entanglement in the parent system. So how do we do that? We already have the von Neumann entropy over here. So you can use the von Neumann entropy, compute that here using the pKs, the probabilities, and by calculating the subsystem von Neumann entropy, you can calculate the degree of entanglement. So it's also called entanglement entropy in that sense. So what are the properties of this measure? So if you have a pure state such as this, then the entanglement entropy is 0 because the probability is just 1. You just plug it here, you immediately see that it is 0. And if you have a pure state and if you decompose it into 2 subsystems, then the entanglement entropy of a subsystem is equal to the entanglement entropy of the complementary system. What do we do? Should I keep talking? Yeah, nice. Okay. Yeah, so as I was saying, if you decompose a system into subsystems, then the entanglement entropy of a subsystem is equal to the entanglement entropy of the complementary system. You can see that immediately here from the way I've written the state. You can see the pKs over here are the same in both these systems. So the entanglement entropy is the same. And one more important property that will be useful to us later is that it is invariant under unitary evolution because you have a trace sitting here, so it is invariant. Okay, so but why is this measure really important? So of course it captures the degree of entanglement in the parent system, but how else is it important? For example, if you take S matrices, you can compute cross-section, decay rates, and all those. But why is this measure important? Because it is a good measure of information. Let's say you have some data AI and it comes with some probabilities PI. And let's say you want to encode this data using certain number of bits. Then you ask what is the average minimum number of bits that is required. Then let's say each one of these AIs come with ni number of bits. So it's like PI ni, and you have to minimize the summation of that. And if you demand that it has to be prefix free, then what you really get is the Shannon entropy. So any less and then you lose information. So it's a good measure of information. Now if you take the entanglement entropy of a joint system, it is usually less than or equal to the entanglement entropy of the individual systems. It is equal if and only if there is no correlation. So this difference which is usually also called mutual information, also captures the degree of correlation. Of course, you can also calculate the connected 2-point function and also quantify correlation. So this immediately suggests to us that entanglement entropy should have something to do with these 2-point functions. So which is what has been explored in this paper. And one more important measure is, let's say you want to see if a system is entangled, a quantum mechanical system. Then you can simply compute the entanglement entropy of the parent system. And if it is less than the entanglement entropy of one of the subsystem, then you can immediately say that there is entanglement. You can see that already here. So we have a pure state here, and the entanglement entropy of this is 0, and this is a completely entangled state. And you have a mixed state over here once you trace out the degrees of freedom, and it is non-zero. So you can immediately say that the system has entanglement. Okay, and it is also important in understanding many-body quantum systems. So let's say your system is undergoing thermalization. Then as the system is undergoing thermalization, the entanglement entropy keeps on increasing, and when it reaches a thermal state, the entanglement entropy saturates. So it's a good indicator of thermalization. It's also a good indicator of phase transitions. So during a phase transition, your system is completely described by a conformal field theory, and the entanglement entropy in this case is completely captured by the central charges that describe the conformal field theory. So in that sense, it indicates phase transitions. So around the fixed point, the entanglement entropy will have a completely different behavior than at the fixed point. Okay. So if you have a finite dimensional quantum system, so let's say you have a quantum mechanical system, then you just have, let's say you have n dimensions, then you have an n cross n dimensional matrix, and you can simply compute trace row on row and get the entanglement entropy. But what about quantum field theory systems? So in quantum field theory system, entanglement entropy is associated with space-like separated subregions. So how do you see that? Take your quantum field theory and put it on a lattice, and you see that it is made up of many interacting harmonic oscillators. So the degrees of freedom is associated with a subregion over here. So it is associated, the entanglement entropy is also associated with such subregions. And if you take a relativistic QFT, then most of the entanglement comes from these local correlations at the boundary. So most of the divergent behavior of such quantum field theories for the entanglement entropy is completely captured by the area behavior rather than a volume dependence. Of course, if you take a non-local field theory, then you will have volume dependence in the entanglement entropy as well. And if you take any two subregions that have the same causal domain of dependence, then they have the same entanglement entropy because of invariance under unitarity. So what I mean by that is, let's say you have two Cauchy surfaces, and this particular subregion has the same causal domain of dependence. Then the states on these two subregions are completely related by a unitary transformations, and we know that the entanglement entropy is invariant under unitary evolution. So for these two subregions, the entanglement entropy will be the same. Okay, now one of the interesting properties that we have in gravitational theories is holography, which we might already know. So what is holography? So if you take gravitational degrees of freedom in a subregion, it is completely captured by a non-gravitating theory on the boundary. And it has been realized concretely in ADS, asymptotically ADS spacetimes. And we have the ADS CFT correspondence, and we had a specific realization that Maldacena gave. So this also comes from black hole thermodynamics, because the black hole entropy goes as the area, so most of the degrees of freedom of the black hole should be on the area, was the idea that motivated holography to begin with. So one can ask the question, so can you compute this field theory entanglement entropy by doing some geometric calculation in the bulk using holography? And this was explored by Ryu and Takanagi in 2006, and the answer is surprisingly yes. So if you have a boundary conformal field theory in the case of ADS CFT, and if you want to compute the entanglement entropy of this subregion, then you can compute that simply by computing the area of a minimal area surface that goes in the bulk and shades the boundary with this subregion. So the entanglement entropy is that minimal area in the unit of 4G. So that is the prescription. So it is surprising that you can simply do a completely geometric calculation to determine a field theory quantity. Okay, so let us see some examples. So let's say you want to do compute the entanglement entropy of a 1+1 dimensional CFT. Then you can put this 1+1 dimensional CFT on the boundary of ADS3, and you can put a CFT2 on this 1+1 dimensional spacetime. And let's say I consider this subregion going between -L/2 to +L/2 on a constant time slice. And the way to compute this is to compute the minimal area surface and in the units of 4G. So in this case, since we just have 1+1 dimensions and I'm restricted to a constant time slice, all that I need to compute is the length of the geodesic connecting these 2 points. So The length of the geodesic in this case is 2r log L by epsilon, where r is the ADS radius. So the entanglement entropy is area divided by 4g, so this geodesic divided by 4g. So you simply get the entanglement entropy has a logarithmic behavior with a divergence that goes as log L by epsilon. So one can also read off what the central charges are in terms of bulk parameters from this calculation. So this was also computed directly in the field theory using by Cardy using twist operator technologies, and this completely matches that calculation. So let's say I have a more complicated setup. So let's say I want to compute entanglement entropy on a d-dimensional space-time on the boundary. So I can do it again in a similar fashion. So I can put this d-dimensional field theory on a d-dimensional conformal flat space on the boundary of ADS d plus 1. And let's say I'm interested in this region on a constant time slice. So R going between 0 and L, spanning these omega directions, these spherical directions. So here I have a compact space. So these omegas are all compact directions. So let's say I want the entanglement entropy of this region. So the way to do that is again to minimize the area that goes in the bulk that shares the boundary with the subregion. So here I have the induced metric. So to calculate the induced metric, I can again see what the RT surface is parameterized by. So in this case, the RT surface is parameterized by the bulk direction rho and these omega directions. And if you want to express this in terms of embedding coordinates in the bulk, so it is simply, so we have a constant time slice and we have R as a function of rho that describes the RT surface, and then you have the XI directions. And you can simply calculate the induced metric simply by using H alpha beta, G mu nu, rho alpha X. So once you have this, all you have to do is to plug this in and calculate the area and minimize this measure. So what you simply have is a Lagrangian problem. So once you calculate the induced metric and plug it in here, you have the area functional, and one has to minimize this area functional. So we simply have a Lagrangian problem. So once you minimize the action, you get certain Lagrange equations that describe the RT surface. Yeah. So you just need the induced metric on an RT surface that goes in the bulk. So I have a specific subregion R going between 0 and L. Yeah. Yeah, it has come out of computation. You have the metric in the bulk. Yeah. Yeah. So the yeah. Exactly. So if you see here, the x mu's are basically these, and you know what g mu nu is in the bulk. It's just ADS d plus 1. So you have x mu's, you have ADS d plus 1. Yes. For now, it's any arbitrary function of rho, and you have to minimize and find the one that minimizes the area. So this is the area functional, and now I have to minimize this, and that will give me a specific R of rho. So once I minimize, I find that R of rho has to solve this differential equation. So there are like two unknown constants, one k over here, and there is a first derivative over here. So there are two undetermined constants, and one has to fix that. So for that, we use the condition that it has to share the boundary with the subregion. So we basically have R of 0 should be 0. So if you have, if rho is the bulk direction going in this direction, and R is this direction, you basically have a branch that comes from here. So you basically have R of 0 is equal to, so rho 0 should be L, and yeah, R of 0 should be 0 and R of 0 should be L. So you have like two branches, and at this point you need R of, let's say this is some rho naught, then you have R prime rho naught should be infinity over here, and then you have the matching conditions over here as well. So the R at rho naught for this branch, let me call it R1, should be equal to R2 of rho naught. So you have these conditions. Yeah, once you impose all these conditions, so this condition basically fixes rho naught in terms of k, and then this matching condition between the two branches fixes rho naught in terms of all the other parameters. So we can get a unique curve by imposing these boundary conditions, and you can plug this curve back into the area functional that I have here, and we have the minimum area. So that minimum area in the unit of 4G is basically the entanglement entropy. And since we get some infinite divergences that come from the boundary of the area spacetime, so I've regulated this using this epsilon, and that goes into the UV regulator that comes for the field theory. So ultimately, I get that the entanglement entropy has this behavior. So there is a divergent V's that goes as epsilon to the power d minus 2, and then the entanglement entropy goes as 1 by L to the power d minus 2. So this can also be read off simply by translational invariance, because flat space has translational invariance. So there should not be any terms such as R1 or R2 just lying around. So there should just be an R2 minus R1 term. Okay. But for more complicated geometries, you have a more complicated nonlinear differential equation that has to be solved to find the minimal area surface. So this is really not a good way to compute the entanglement entropy. So let's say I want to compute the entanglement entropy on ADS3 for a CFT3. Then I can again do that by putting by considering a conformal ADS3 on the boundary of an ADS4 symmetric, and I can put a CFT3 on this ADS3 spacetime. So I have an ADS3 spacetime which is conformal, and this is an ADS4 symmetric. Now again, I can consider a similar entangling surface, and I can ask what sort of surface minimizes it. And you can immediately see from here that this is a completely nonlinear differential equation. So instead of considering a flat background, if I simply consider an ADS3 background, I already run into issues. So one can only say solve this numerically and cannot solve it analytically, or maybe one can use analysis at the boundary to solve this asymptotic analysis, but that's all one can do. So one needs some other way to compute entanglement entropy. But before going into that, our main focus would be black hole thermodynamics. So let me quickly talk a bit about that. So in the early days when people noticed black holes, Birkenstein had this question. So what if I throw something into a black hole? Then simply by throwing, I can reduce the entropy of the whole universe if the black hole does not have an entropy. So this led Birkenstein to believe that the black hole should also have an entropy. And around the same time, Hawking just proved the area theorem, that the area of a black hole should always be increasing. So Birkenstein took inspiration from that and proposed that the entropy of a black hole should be proportional to its area. And since we are computing a thermodynamical quantity, we have a KB over here, and we have L Planck over here for dimensional grounds. But when Birkenstein actually calculated this, he did not fix this 1/4 constant. Later, Hawking actually did a semi-classical analysis, and he showed that the entropy of a black hole actually goes as the area, and he fixed this constant to be 1/4. And this also shows us that the temperature of a black hole should also go as 1/m. So black holes are indeed thermodynamic objects, but then if you incorporate quantum mechanical effects, the analysis that Hawking did, you immediately see that the area of a black hole can actually decrease because it loses mass by emitting Hawking radiation. So if one has to preserve the second law of black hole thermodynamics, then what one must actually consider is the generalized entropy and not just the area behavior of the black hole horizon. So one has to consider the sum of the area of the horizon plus the entropy of the quantum fields. And this is what one must associate the entropy of the black hole to. So this immediately suggests to us something called the central dogma. So what I mean is you can completely replace a black hole by degrees of freedom on the surface of the black hole. And these quantum degrees of freedom must evolve unitarily and completely describe all the bulk physics of the black holes. So this is in a way the same as the holographic principle. So except all the degrees of freedom are not at asymptotic boundary, but are on the black hole surface. So if you assume this central dogma, then one can immediately see that you run into a paradox. Let's say I start with a black hole in a pure state. So on the surface of the black hole, I have certain pure states. And as the black hole evaporates, it loses mass. So you can see that the temperature of the black hole goes as 1/m, and the area goes as m square. So you have a 1/m square dependence from Stefan-Boltzmann law. And so the black hole actually loses mass, so it loses area. So the entropy of the black hole is decreasing. But however, from Hawking's semi-classical analysis, we know that the radiation that comes out is completely thermal. So let us look at the two extreme ends. So initially you have a pure state, so the entropy is 0. But then once the black hole has completely evaporated, you just have thermal radiation. So you have a completely mixed state. So you have gone from a pure state to a mixed state, and for a mixed state, that the entropy is non-zero. So you really have non-unitary evolution over here because the entanglement entropy cannot change under unitary evolution. But then the problem comes much before. So that can actually be seen by seeing the fine grain versus coarse grain behavior of the entropy of the black hole. So we know that the coarse grain thermodynamic entropy of the black hole goes as the area. And since I already showed you before that the entropy of a system is equal to the entropy of its complement, if you start with a pure state, that must also apply over here. So since I started with a black hole in a pure state, the entropy of the radiation should also be equal to the entropy of the black hole that is left out. So as more and more radiation comes out, the entropy of the radiation keeps on increasing because you have a thermal radiation. But at some point, the entropy of the radiation becomes much more than the area entropy of the black hole. But the entropy of the radiation is also equal to the entropy of the black hole, which means the fine-grained entropy of the black hole is more than the coarse-grained entropy of the black hole, which means there's not enough degrees of freedom in the radiation to actually entangle and purify the black hole. So since there's not enough degrees of freedom in the black hole, so you basically run from a pure state to a mixed state at this point, which is called the page time. So the problem really starts at the page time and not really at the extreme ends. But this also suggests to us what one must consider if you need to have unitary evolution. So we need the entropy of the black hole to always be bounded by the area entropy of the black hole. So then you have unitary evolution. So one must expect a curve that looks something like this triangle, and this is called the Page curve, which Page proposed in 1980. So this is the curve one must expect if we need to have unitary evolution. So can you somehow motivate from holography certain quantum corrections that actually bring down the entropy of the black hole? So that really seems possible. So before going there, let us try to ask what is the quantum corrections to a boundary field theory entropy. So we just saw that the entropy of a boundary field theory in a subregion goes as the area. But then if you want to add some quantum corrections, what you really need to consider is not just the area piece, but also the quantum field theory entropy. So you take the sum of the area piece and the quantum field theory entropy and then minimize for the sum of both. That is the generalized entropy. And you get new candidate extremal surfaces, which are called quantum extremal surfaces. And it is this quantum extremal surface that one must consider. And the generalized entropy bounded by that is what captures the quantum corrections to the entropy of the boundary subregion. So one can now ask the question, since the boundary field theory is unitary, can you somehow get unitary evolution in the black hole as well by this consideration? And the answer seems to be true, and even it seems to be true purely in a semi-classical sense. So earlier it was believed that one needs quantum gravitational effects to actually restore unitarity in black hole evaporation, but that does not seem to be the case. One can simply use semi-classical analysis and certain quantum corrections to actually restore unitarity. So this is called the island prescription, which I'll describe now. So you do the same thing even in the case of a black hole. So you consider subregions in the bulk of the black hole spacetime, and then you consider the generalized entropy in that subregion, and you minimize the generalized entropy for candidate subregions. So you get different subregions, and there will be one subregion that has minimum generalized entropy. So one must consider that subregion, and the generalized entropy of that subregion is the entropy that must be associated with the black hole. So this is the next sort of revolution after the entropy of the black hole that I showed here that preserves the second law. So here, instead of just considering the generalized entropy, you must consider the minimum of the generalized entropy. And that is what must be associated with the black hole. For my setup, I'm just doing just over space, but in general, one must do over space and time as well. Yes, yes. So there'll be like two conditions, one over space, one over time. Yeah, yeah. So, but then, so you get different subregions, and if this subregion is not all the way at asymptotic infinity, then you have a subregion that is finite. And if I start with a pure state, then the entanglement entropy of, say, this subregion is equal to the entanglement entropy of the complementary subregions. So you suddenly get a region that is completely disconnected from the asymptotic boundary, and this is what is called island. So if you simply consider the area piece and minimize that, then you would simply get the entire Cauchy slice. But then if you minimize the generalized entropy, you get a finite subregion, and that is what brings in the island. That is just a time-like curve. It has no significance now. I'm just showing a time-like curve. Yeah. No, if you simply consider the area and minimize that, then the area is of course minimized at r equals 0, right? So then you would get the entire Cauchy slice. So you need to collect the radiation over the entire Cauchy slice. But then if you minimize the area piece plus the quantum field theory entropy, then it is usually minimized in a finite subregion and not the entire Cauchy slice. And the entanglement entropy of this finite region is equal to the entanglement entropy of the complementary regions. So you have a piece that is completely disconnected from the asymptotic boundary, which is called islands. So it is actually the correlation between degrees of freedom in the island and the region connected to the asymptotic boundary that actually brings down the quantum field theory entropy and brings down the page curve in the later stages of black hole evaporation. So that is the sort of intuition that we need to carry around. But I must also tell you that these islands actually come after the page time. But why do they come after the page time? Because the islands actually bring with them an area cost. So we are minimizing the sum of the area piece plus the quantum field theory entropy and not just the area. But then these bring an area cost. But then if you naively just take a 0 length subregion to minimize the area cost, you'll actually miss out on paired modes. So the quantum field theory entropy will increase. So the generalized entropy won't be minimized as a whole. So the reduction in the quantum field theory entropy actually dominates the area piece that is added, and in the later stages of the black hole evaporation, when more paired modes are produced. So in the later stages, after the page time, these islands appear. And if you also look at the location of the islands, of course, the islands bring an area cost, but then if you simply reduce the area cost again, you will again miss out on paired modes, and so the quantum field theory entropy again increases. So there is an interplay between the quantum field theory entropy and the area piece, and a balance between both has to be struck, and that is struck at the quantum extremal surface. So yeah, is this fine? It's usually one extremal surface. Yeah. Maybe I can interpret your question as, can there be more islands, more than one island? Yeah. Okay. But however, this is a statement about how entanglement entropy has to behave. Can we somehow translate this statement into a statement about correlation functions, about the quantum field theory spectrum? So that is the question that we had. And that actually seems possible, because what we really need is to minimize the generalized entropy. So we took a static black hole background in this gauge, and let's say I consider a subregion R going between R1 and R2 on a constant time slice, spanning the omega directions, all the spherical directions. And let's say I want to minimize the generalized entropy. So to minimize the generalized entropy, there are certain conditions that I have to impose. And if I demand that this quantum extremal surface is at a finite point so that I get islands, then there are certain conditions on the first derivative of the generalized entropy, that this has to be at a finite point. And there are also conditions on the second derivative if I demand a minima. But what one must notice here is that the quantum field theory entropy completely has the information about the quantum field theory spectrum, and the area piece is completely geometrical. So these conditions are actually conditions on the quantum field theory spectrum in terms of geometrical quantities in the bulk. So if one is able to calculate the quantum field theory entropy, one can actually impose conditions using this on the quantum field theory spectrum. So that is the idea. But then the catch over here is that calculating the quantum field theory entropy is usually hard. I already showed you that if you want to do a RT analysis, if you simply put a CFT3 even on an ADS3 background, you run into nonlinear differential equations that you have to solve for the RT surface. So even if you want to do a field theory computation, it is really hard. So there's a huge gap in literature. So we usually know the quantum field theory entropy for CFTs in 1+1 dimensions. There are certain results that we know in 2+1 dimensional flat space background for a CFT again. We do know some universal features in general dimensions. So for example, we know that the divergent piece must go as the area, and these come from considerations such as locality. And we do know for say vacuum state on a flat background. But then, as I was telling you, the RT surface that describes, that captures the entanglement entropy is described by a nonlinear differential equation, even for a ADS3 background. And we need it on a black hole background. So it is going to be much more complicated. But then the saving grace for us is something that condensed matter people have been exploring for a really long time. It is called the replica trick. So instead of computing the logarithm of an infinite dimensional density matrix, which comes in the von Neumann entropy, what I will really do is consider q powers of the density matrix, and then I take the trace of that. So this will really give me a number, and then I take the logarithm of that number, which seems easier. And then what I really need is the negative of the order q minus 1 piece of that. Why is this? This is called the Rényi entropy, Rényi q entropy. Why is this important? Because if I take the q tends to 1 limit of this quantity, of this Rényi q entropy, what I really get is the von Neumann entropy. So this is an indirect way to actually compute entanglement entropy. But then have we really simplified the problem? Let us see that by asking what this trace rho par q is. So this trace rho par q is actually the generating functional on a q-fold replicated manifold. You take q copies of the manifold, take the subregion that you're interested in, and you take cuts along the subregion that you're interested in, and you identify the top cut with the bottom cut cyclically, and then you get q-fold replicated manifold. I'll refer to this as the replica manifold from now on. And then the partition function on this q-fold replicated manifold is what this trace rho par q actually captures. So to be more precise, the trace rho par q is equal to zq on the replicated manifold, and if you normalize, then you also have a z1 whole par q, where z1 is the partition function on the one manifold. So this is what we really need, and we need the logarithm of that. So if you take the logarithm of that, then you simply get the connected generating, the difference in the connected generating functional on the replica manifold minus q times the generating functional on the base manifold, on the original manifold. So I've just simply taken a logarithm of this to get that. And since I'm taking a q tends to 1 limit to get the von Neumann entropy, I simply need the order q minus 1 piece and need the negative of that to compute the von Neumann entropy. Okay. So as I was telling you, entanglement entropy in a field theory is associated with space-like separated subregions on some Cauchy slice, right? So you take some constant time slice, and you make, by cuts, what I mean is you take a t plus epsilon, t minus epsilon region, and then you identify the t plus epsilon cut with the t minus epsilon cut in the neighboring manifold. And I keep doing that cyclically. Yeah. So what we have not really simplified the problem, we have really traded difficulties, because computing this zq, the partition function on this complicated manifold, is really hard. So which is the bottleneck in computing, even using field theory, the entanglement entropy. But then what we do not really need the complete von Neumann entropy. The conditions that I showed you is actually d by dr of SQFT and the second derivative of SQFT. So I really need how the quantum field theory entropy scales with the subregion, or not, and not the quantum field theory entropy itself, to talk about black hole physics. So I'll be focusing on that. And specifically, I'll restrict to CFTs on a static background. So once I restrict to that, the only scale in my theory is the length of the subregion itself, delta r. And I can ask how the entanglement entropy changes if I scale this subregion. And that completely depends on the renormalization scale, how the SQFT changes with the renormalization scale. And if you restrict to a CFT, the variations with respect to the coupling constant and the beta functions vanish. And what you are left with is the variations with respect to the metric itself and the variation of the metric itself with respect to the subregion. So the variations with respect to the metric of the connected generating functional gives you the stress tensor 1-point function on the replica and the base manifolds. And then you have the variation of the metric itself on this replica and the base manifold. So that is what we really need. You can also ask a more general question. So let's say I don't want the behavior of the entanglement entropy with just scaling delta r. I need a more general scaling. I need some symmetry transformation. One can also incorporate that. But in this case, you simply have a Lie derivative instead of the variation of the metric with respect to delta r. So you can play around for more general variations as well in this setup. But then so let's say someone gives you a Lagrangian, and let's say someone gives you the background, then you completely know what the stress tensor 1-point function is, and you know the metric on the base manifold. But then what about the stress tensor 1-point function and the metric on the replica manifold? So let us see what that is. So I told you that on the replica manifold, you have the cyclic boundary conditions. So let us focus on the bulk and on the boundary of this subregions. We see that in the bulk of the space-time, if you actually do the replica boundary conditions, then by this identification, you simply recover q copies of the same manifold in the bulk. So I've just identified the yellow region with the orange region over here, and this orange region with the blue region over here, and the blue region with the yellow region over here. So in the bulk, I simply get q copies of the same manifold. But then all the interesting things happen in the boundary of the subregion. If I identify the boundary of the subregion using these replica boundary conditions, then what I really see is that I get a cone with an opening angle of 2 pi q by these identifications. So all the interesting things happen at the boundary. So the metric remains the same everywhere except at the boundary of the subregion, where it actually picks up a conical singularity. So if I take my static metric, I can expand my static metric around the boundary. So if you forget about what I've shown in blue over here, this is simply an expansion of the static metric at the boundary of the subregion. And I have used parameters that are useful for me. So here rho is the distance from the endpoints and psi is the angle around the endpoints. And since I have a conical singularity around at the boundary, so the angle actually goes between 0 and 2 pi q. So that captures the conical singularity. So this is a conical singular metric once I allow psi to actually go between 0 and 2 pi q. So this is the metric around the boundary of the entangling regions. So one can actually regulate this conical singularity by using appropriate regulating functions and a regulating parameter. So if you're far from the endpoints, then this should simply give me the original metric. So this has to go to 1. And if I'm really close, then this conical singularity has to vanish, which means this has to go as q square. So there are several functions that actually do this. And whatever I calculate, let's say I calculate entanglement entropy, it has to be independent of the choice of the functions that I make at the end of the day, once I send the regulator to 0. So I have a conical singular metric at the endpoints. So I know what the metric is. But then let me quickly remind again that the entanglement entropy actually depends on WQ minus QW1. So all the information about the conical singularity is in this difference of the connected generating functionals. So it will actually be useful to do an order Q minus 1 expansion around the boundary. And once you do that, so we have the metric expanded in parts of Q minus 1 and the stress tensor 1-point function on the replica manifold expanded in parts of Q minus 1. So just notice the notation over here. This is the order Q minus 1 correction. So now one can, since you know what the metric is, you can go ahead and compute what the stress tensor 1-point function is on the replica manifold. To calculate this, I've simply used the conservation equation on the replica manifold. So since I know the metric, I can use the conservation, the covariant derivative is known. So I can use the conservation equation. This gives me D equations. And if I restrict to a CFT, because of dilatation invariance, the trace of the stress tensor should be equal to the anomaly, which completely depends on the replica metric again. Since I know the replica metric, that gives me one more condition. So I have D plus 1 equation, and I have D into D plus 1 by 2 unknowns, since I have a symmetric stress tensor on the replica manifold as well. But then if I restrict to a static background, then all the cross terms such as T rho I, T psi I, and T ij's vanish. And I really have D plus 1 unknowns and D plus 1 equations. And these D plus 1 equations completely determine the D plus 1 unknown replica stress tensor components. So I know all the quantities over here. So I know the replica stress tensor, and I also know the replica metric. And one must simply compute this difference by simply doing an expansion in parts of Q minus 1. So if you see the expansion over here, so I just have the order 1 piece is simply equal to the stress tensor 1-point function on the base manifold. So that immediately gives me certain cancellations over here. And what I ultimately end up is that the scaling of the entanglement entropy with respect to the region actually depends on the order Q minus 1 stress tensor correction, which I just calculated now, and the scaling of the metric itself on the subregion, on the one manifold. So I know all these quantities, and this quantity is completely determined from the conservation and trace equation in terms of stress tensor 1-point function on the base manifold. So the scaling of the entanglement entropy depends on stress tensor 1-point functions on the base manifold and the scaling of the metric itself ultimately. So as a proof of principle, we can calculate the entanglement entropy for CFT on a d-dimensional flat space for a vacuum, and you can see that the stress tensor, the replica stress tensor, goes as 1 by rho par d in this case, where rho is the distance from the endpoints, and the scaling of the entanglement entropy goes as 1 by delta r to the power d minus 2, which I also showed using the RT calculation before, and this matches that. And if you have a thermal state, then you also have a pressure term that goes as P times delta R squared. So you can also take more complicated static backgrounds, more complicated states, and use this expression to actually compute the entanglement entropy explicitly, the scaling of the entanglement entropy. So ultimately, the scaling of the entanglement entropy depends on the stress tensor one-point functions. And I showed you that the conditions for islands over here depends on the scaling, right? So now I can take the expression for the scaling and plug this in over here. So this actually imposes constraints on the stress tensor one-point function in terms of geometric quantities that are sitting in the area piece. So ultimately, we have condition on the stress tensor one-point functions if there has to be an island and if we have to preserve unitarity. So that is the idea. Yeah, so now, for example, we have calculated entanglement entropy for QFT on flat space and for thermal state as well. So I can take that and I can see if there are islands. And surprisingly, even for a thermal state on a flat background, even when there are no black holes, there are in fact a finite quantum extremal surface and islands. And even if you have a CFT in even dimensional flat space time, you again have an island. So it seems like whenever you have a dimensionful parameter, such as pressure term over here, or if you have anomalies, you do end up getting islands. So most of the calculations for islands were in 1 plus 1 dimensional JT gravity, where there's actually a central charge term because of the anomaly. And it is because of that we suspect it is because of that there were islands even in 2 dimensions. Because there's no black holes at all. So, and these quantum corrections actually apply for black holes. Here I just have flat space. So why are there islands over here? I would expect there not to be an island. Because, okay, from my perspective, the presence of islands is to actually capture these paired modes that are hiding behind the horizon and bring down the page curve. But then if you just take flat space, all the radiation is available outside. There's no horizon shielding certain modes. So I don't see the necessity of an island for unitarity in flat space.
This ER into DPR thing was correct then. Then in flat space you expect these wormhole geometry to be there, even in the absence of you expect
I mean, from a wormhole, purely wormhole sort of calculation. Yeah, maybe, but physically, I don't see the need for an island because all the radiation is available at asymptotic infinity. There's nothing like a horizon shielding some radiation, right? I mean, one has to go through the calculation of the wormhole to see if it is at a finite point. It's not trivial, right? So there's a lot of interesting future work one can do. As I was saying before, even without the black hole context, we have given a way to compute the scaling of the entanglement entropy in general dimension for a static background for any state. So once someone gives you the stress tensor one-point function for any theory that you want on a static background, you can simply take that and compute the entanglement entropy. So one can go ahead and compute for more complicated states and backgrounds, general static backgrounds. One can extend this to stationary spacetimes. So over there, you don't have spherical symmetry. So one has to also take finite subregions in the theta and phi directions, for example, and that might reveal more interesting physics. One can also consider spacetimes that do not have a time translational symmetry. So this becomes relevant in de Sitter holography, where instead of considering space-like separated subregions, people also consider time-like separated subregions. It is not really clear what the quantity actually measures over there, but one can compute there and see if there is some sort of a holographic picture over there, which people are exploring now. Now there's a lot of interest in Carolean and celestial CFTs, which are putative dual to flat space scattering. So one can again go there and compute the entanglement entropy on these null surfaces where the Carolean and celestial CFTs live. And just like the RT formula, one can see if there is a RT formula over there as well. So I showed you that I computed this stress tensor on the replica manifold using the conservation and trace equations. So that will be modified over here because we have a degenerate metric. So apart from that, I don't see any other difference over there. But of course, one should also interpret what the entanglement entropy even means on these null backgrounds, and if there's a holographic proposal. But the interesting thing for us is to actually compute this entanglement entropy on static backgrounds and see what the explicit constraints on the stress tensor one-point functions are. So that is what we are exploring right now. So there's also something called the quantum focusing conjecture that also talks about how entanglement entropy behaves for null geodesic congruences. So one can see if these quantum corrections to this focusing conjecture can be refined further, since we have a direct way to compute the scaling of the entanglement entropy. So there's a lot of interesting directions one can explore from this. Yeah, thank you. Yeah. Mm.
Way of doing things is that you're assuming that you're allowed to take the Q into one limit. The replica geometry is only defined when Q is an integer.
Yes.
Then you're analytically continuing Q into one.
One, yes. Yeah.
So that means that it's also valid for Q equal to 1 plus epsilon.
Yes.
That means that you're actually assuming that the condition for Carlson's theorem holds.
Yeah, it's analytic. We expect it to be analytic. Yes, it's. I don't think it's completely proven. In fact, for spin glass systems, it breaks, right? Yeah, there are certain systems. Yeah, but usually when people do this quantum mechanical calculations, they know exactly what the density matrix is, and then they just plug it into a computer and compute the von Neumann entropy. Yeah. Yeah. Yes. Yeah.
When you have a regularized conical geometry.
Yeah.
In your way, you cannot actually calculate it for integers.
Mm. Yeah, exactly. Yeah, because I'm just computing a partition function. Yes. So I am assuming certain analyticity properties for the field theory. And I think the Q going to one limit not being, I mean, it not being analytic around Q equals one is usually for certain exotic systems like spin glass systems. I mean, I was discussing this with Subir as well, and that's the opinion Subir had. So for well-behaved quantum field theories, he expects that it will usually be analytic. But of course, no one has shown it rigorously using a mathematical proof.
For any Q. So you actually require to define the geometry that you define.
Yeah.
You have this regularization function.
Yes.
Q in your metric.
Yeah.
So they exist and they capture the correct Rényi entropy.
There has to be some other independent way, I feel. Because even the way I'm doing, I'm assuming the analyticity properties when I actually do that, right? So I feel there has to be an independent way of computing the field theory entropy that is independent of this replica trick itself.
Right.
Yeah. 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 This is something I generated using ChatGPT.
ChatGPT, which one?
4.0. Yeah. 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 If you have any questions, any more questions, yeah. Yeah. The bulk fields. Yes. So if I go back to, so I have a boundary field theory and I want the quantum corrections. So the area piece is like the 1 by h bar piece in the entanglement entropy. Now I want a h bar to the power 0 piece. So that actually comes from taking the quantum field theory entropy bounded by this surface and the subregion in the boundary. So it's actually the bulk fields. One must use something like the replica trick to calculate it. There's no other way. Yeah. Yes. No. You can use replica trick for any field theory. You don't really need to. It's a completely field theory computation. It has nothing to do with holography. Yeah. Or what you can do is take this. Let's say this is some 4-dimensional spacetime in the bulk. Take this and put it on the boundary of some 5-dimensional spacetime, and then compute like the SQFT, and then plug it back here and get the quantum corrections. You can do that as well. Hmm. Yeah. Okay. Okay. You are asking why are black holes special in a sense? I mean, what changes in a thermal system as opposed to a black hole? So yeah, that is what I was saying now. So in a black hole, the presence of the horizon is what is special. So you have certain degrees of freedom inside the horizon, which are not accessible to an observer at infinity. So somehow the entanglement structure between degrees of freedom inside and outside has to be different as opposed to some thermal system. Let's say you have a fire burning here, then all the modes are somehow available to the person at infinity, right? So the entanglement structure should be different as compared to a black hole to actually restore unitarity. So that is the key difference over here. Yeah. Yeah. Yes. Yeah. That's what I expect. Because everything is available at infinity. Sorry? Yeah, which is surprising. Yes. Yeah, in a sense. I mean, these are on shaky grounds in a sense, right? So, yeah. Maybe if you consider 1 by h bar square corrections, maybe something might change. Sir, I didn't understand your question. Yeah. I mean, that is the motivation to actually apply the quantum extremal surface prescription in the bulk. Yeah. He's asking just because the boundary field theory is unitary and the boundary field theory is dual to something in the bulk. So does that imply bulk unitarity? Yeah. Yeah, there's no proof of that. So. Yeah.
Unitarity sort of was a spectator in all the calculations that you described.
Mm.
Did not play a key role anywhere.
I think when I demanded, let me see, when I demanded this condition that the quantum extremal surface should be at a finite point, that's where unitarity played a role. I mean, basically, I'm demanding that islands have to exist, which means unitarity should somehow be restored. Yeah. Thank you. Yeah, you can always bug me with more questions whenever you want. It's just the position of the two quantum.
Sorry, you got the quantum extremal surfaces exist, but when you actually plug it back to your formula, what does it actually contribute?
So here nothing is evolving. Don't really have anything evolving.
No, but this is contributing to your entanglement, right? What does it contribute to your entanglement?
So I take the generalized entropy bounded by this between x1. Okay. Yeah. Actually, so there's a 1 by delta unitarity. So basically this. So this is the concrete theory, and then there's an A at least 4 by. So really consider black hole, one has to consider the operating setup. Then you get all the time equation. So what I'm assuming here is some sort of quasi equilibrium.
And the punchline of your talk is what? You find these external surfaces where there is no black hole. Is that the punchline?
The punchline is that scaling of the sphere field depends completely on the stress of the. So once I flip it back over here, I get conditions on the system. So there are constraints on the system.
And reverse engineer theories where this condition is valid.
Yes. Yeah. Particular quantum.
And you have examples of that kind where this condition is violated. And you see that something like this single charge is negative or something like that.
Take any odd dimensional sphere. Then there's no anomaly.
Sorry, and what does it imply for dimensional safety? What does it imply for dimensional safety? I have some ordinary unitary steady state.
Yes.
And you're saying that
If I have some odd dimensional black hole, the safety on top of it.
but then what is the resolution of the information paradox?
We don't. You probably have to take, it's not described. The radiation of it has to be described by certain QFTs that do not.
These Bayesian geometries where we know the duality very it's ADS4 and then you have a CFT3, it's a super so there is the black holes here.
But I'm taking the free theory about it, right? It's a condition of the free theory.
Oh, I see. So then it's but even better.
Yeah.
Because then what happens for ADS5?
That's okay.
Field theory in ADS5. You are saying that what is it that is?
In the bulk, the radiation should be described, the outgoing cosmic radiation should be described only by particular. It can't just be.
I see. So it cannot be a CFT that describes.
It cannot be. It has to be particular QFTs that obey this.
Okay. That is not happening.
Yeah, we are getting like specific numbers. When we have exact. And also, you have some work on minimizing entanglement.
Right. Yeah.
So this is sort of very similar. One thing is, I think I was discussing with Arvind also. If there is some sort of first principle interpreting entangled locality, motivating why the entanglement must be exactly doing that for black hole.
Philosophy was of course a little different. It was just the difficulty of making entangling gates in the lab. So minimize the number of entangling gates that are there. Related to the sort of complexity thing we are doing. So basically, consider only those processes where entanglement is
Because it's more intensive.
yeah, because it's more cost costly to have.
Can we try something like because here unitarity is what is maybe that's something to do with unitarity over there. Yeah, and the way I discussed here is, I mean, I'm relating correlation functions to the map. The minimization should be something for
1 point.
1 point. But if you take any Q entropy, this will be a Q plus 1 point. We talk about minimizing any Q entropy or something. Actually, this is not even a 1 point function, it's actually a 2 point function in this case. Because a 1 point function on the replica manifold is 2 point function. So we take the correlation function between this on the base manifold and the modular. Thank you.
Since your PhD student, you're finishing this year. Your what's the postdoc straight? 2 year applying. The constitution is going back towards. I think you should do some macro constitution. Yeah, learn a different skill. Machine learning. Because at least constitution in India is absolutely hard. There will be like very soon with like 30 or 20 lines of constitution. Not like this one. I mean, like it could be like one position there, right? Because of the pattern? No, because of the fact that nobody cares about everything is integrated into concept. So that you're relevant in that area, then very different. The new IITs, because I'm on the academic evaluation committee, I know that so first of all, they probably will hire one because they want to teach some basic. But the funding is all redirected there. What? That is what has been happening. Yeah.